Swayam Prabha. Digital India. Educated India.
Okay, in the last lecture we have seen how to solve two-dimensional plane truss and three-dimensional space truss problems, and basically in both of these, knowing the orientation of a truss member and knowing the extreme points, extreme ends of a truss member, we calculated direction cosines, and using the direction cosines and material property, geometric properties of a particular truss member, we assembled element stiffness matrices for each of the truss member, and then based on the element connectivity, that is for each truss element based on the node numbers of the extreme ends, we assembled the global stiffness matrix, and later we imposed essential boundary condition, that is displacement based displacement boundary conditions, and in addition we also make or we also made sure that the loads were applied at the appropriate locations in the global force vector, and we solved the reduced equation system after applying the essential boundary condition, that is displacement boundary condition. We solved the reduced equation system, and we got, once we obtained the unknown displacements, we went back to each element and we calculated strains, stresses and the loads on that particular truss member, and knowing the global displacements, we calculated local displacements using transformation matrix. In this exercise, two things I want to emphasize. First thing is we applied loads at node arbitrarily, that is the loads can be applied at a node arbitrarily. Loads applied at a node can be arbitrarily assigned to any of the elements connected to the node. So this is one concept or one thing, and the other thing is the terms in the global stiffness matrix corresponding to the nodes with zero displacements have no influence in the final system of equations. So to minimize calculations, we ignored rows and columns corresponding to zero specified displacements, and if the specified displacements are non-zero, then we actually need to need the columns corresponding to those specified degrees of freedom, because actually they, using those we calculate some contribution, and also they help us to calculate the reactions. So with that we will start looking at the stresses due to lack of fit and temperature changes in truss problems, and usually these stresses are induced in indeterminate structure in the indeterminate trusses due to temperature changes in some elements, or because of force fit if an element is fabricated too short or too long. So both kinds of problem, that is if you want to solve a problem to determine stress truss problem, to determine stresses due to lack of weight and or temperature change, the procedure is almost similar. So both situations can be analyzed in a similar manner by applying force equivalent to the change in the length of the element. So let us see what happens. Suppose an element of length L is fabricated too short by an amount delta L, that is, first we are going to look at the stresses, how to compute the stresses due to lack of fit in a truss member. So let us say an element of length L is fabricated too short by an amount delta L, and if the element is fabricated too long by amount delta L, then it is just we need to change this sign, then it becomes negative of this, that is minus delta L, and the tensile force would be required to make this element fit into the structure, because the member is long. So to fit this truss member into the given a particular structure, we need to apply some tensile force, because it is too short. So we need to just stretch it. After this element is put in place in this structure, that means a member is too short, and this member is by some means it is stretched and it is placed in the structure. And what this member will do when it is put in the structure, it will exert an equal and opposite force on the entire structure. So this is what is expected. And suppose if the instead of a member being too short by a certain amount, if it is a little bit longer by a certain amount, then we need to apply some compressive force to fit force fit into the given structure. And what this will do is, when you force fit, it actually applies the member will be under compression, and in turn that member in turn will exert an equal and opposite force, which is going to be tensile force if it is too long. And now since the member is too short, the member will be under tensile force, and whereas it is going to exert a compressive force in the structure. So the analysis corresponding to these forces proceeds in the usual manner, except that at the end, when we are calculating element forces, we need to add the forces due to lack of fit. So final element forces in the element with lack of fit are superposition of initial forces and forces computed from analysis of the entire structure. So for plane truss problems, the equation looks like this. The first term Pft is nothing but the force that is required to stretch a member or to compress a member to force fit into the given structure, and this is for plane truss. But rest of the analysis proceeds in a similar manner we already looked at in last class. For space truss, the equation looks like this. Again the additional term is here, Pft is nothing but the force due to force fit. And now how to solve problems because of change in the temperature. We know that change in the length of a bar subjected to a temperature of delta T is given by delta L is equal to alpha delta T times L, where alpha is coefficient of thermal expansion, and delta T is the change in the temperature, L is length of original length of the member, and this change in length of element can be treated in a similar manner as that of lack of fit, because now because of temperature change there will be change in the length of the member which exerts some kind of force on a given structure. So analysis proceeds in a similar manner as that of lack of fit. So now let us take a problem to understand the various steps involved. A plane truss problem. Find displacement and axial forces in the truss shown in figure below if element 1 is fabricated 4.5 inch, corresponding SI units in millimeters are also given. The element 1 is fabricated too short by an amount 6.35 millimeters or 1/4 an inch, and is forced to fit assembly, and this member is too short and by some means it is stretched and it is force fitted, and we need to analyze this plane truss for displacement and axial forces. Material properties are given, E and cross sectional area of members, all members are of same cross sectional area and they are given in the problem statement, and here 10 is feet. So, the dimensions are indicated there. And let us see what this member is going to do. So, figure B shows that actually the truss member which is short will be by some means it is stretched. So, it will be under tensile force, and this member in turn will exert an equal and opposite force which is shown in figure C. So, this member is actually going to exert a force as shown in figure C on the structure. So, what we need to do is we need to proceed and solve the problem which is shown in figure C for after calculating P F T, and for those forces and for the given orientation of truss members, we need to solve the problem and find stresses and displacements. And once we get those values, what we need to do is we need to superpose the values that are given in figure B. So, that is how the solution proceeds. So, now let us look at the details. Element equations. So, we need to start with element 1. Element 1, the local node 1 is same as global node 1, local node 2 is same as global node 4. So, element 1 goes from node 1 to node 4. So, we need to, looking at the problem, we need to find the coordinates of node 1, x1 coordinate, y1 coordinate, and x4 coordinate, y4 coordinate. And once we have these values, we can find what is dx, which is nothing but x4 minus x1, and dy, y4 minus y1. All the quantities here are given in inches, because each member or the dimensions are given in inches and feet. Feet is converted into inches, and length of member is given by dx square plus dy square, square root of that. And once we know these values, we can find what is cosine alpha and sine alpha, and here both are same, and it is given there 0.7071. EAOL is also calculated based on the material property, Young's modulus. Cross sectional area of member is given. So, once we know length, we can calculate that quantity. So, this is for element 1, which is going from node 1 to node 4. So, to have a better idea, let us go back to the figure and see. So, this is if you see figure A, there member element 1 is connecting nodes 1 to 4. So, just now we calculated the corresponding direction cosine values for that element. Similarly, element 2 is going from node 2 to node 4, and element 3 is going from node 3 to node 4. So, we can calculate for those also in a similar manner, and the global x coordinate and y coordinate are defined at node 1. That is why the nodal coordinates of node 1 are 0, 0, and nodal coordinates of node 4 are 10 feet times 12, that is 120 inches. X is 120, y is also 120, and nodal coordinates of node 2 are 0 and 240, and the nodal coordinates of node 3 are 120 and 240. So, we have already seen for element 1 what are the values, and once we have these values, we can actually assemble the equation system, element equations for element 1, and transformation matrix is given by this, which is CS0000 CS, and local stiffness is given by EA over L 1 minus 1 minus 1 1, and once we have the transformation matrix and local stiffness matrix, global stiffness matrix is given by T transpose KLT. So, that is given by this one. And this member 1 is short by length 1/4 inch. So, the force P of T due to lack of fit we can calculate for this member E A over L delta L. Delta L is 1/4 inch, all are in inches. So, 1/4 is substituted, that is 0.25, and it is calculated. The value both in FPS units and SI units in kilonewtons are given there, and this represents tensile force in element 1 as shown in figure B, which you already looked at. When this element is placed in the entire structure is under an equal and opposite force. We have already seen that, it is shown in figure C. So, element load vector is in the local coordinate system at node 1, PFT is acting in the direction of the member, that is 0 to local, it is acting from local in the direction of local node 1 to 2, or it is acting in the direction from node 1 to 4. So, the first component is positive and the second component is acting in the opposite direction. So, it is negative sign is appended to it. So, in the local coordinate system RL is given by this. So, we already know what is transformation matrix. So, we can calculate what is the in the global coordinate system, what is the load vector. And please note that here we are assigning loads, given loads to member 1. So, all the loads were assigned to only member 1. So, they are given here. For element 2, local node 1 is global node 2, local node 2 is global node 4, and it is assumed to be going from node 2 to node 4, and noting down the coordinates of node 1 and node 4, we can calculate what is dx dy and length of this member, and also once these values are known we can calculate what is cos alpha and sin alpha, and also EA over L. Once we have all these quantities, we can calculate what is transformation matrix and what is local stiffness matrix and global stiffness matrix. K is given by T transpose KLT, that is given by this one. Next is element 3. Element 3, local node 1 is global node 3, local node 2 is global node 4, and element 3 is going from node 3 to node 4, and noting down the coordinates of node 3 and node 4, we can calculate what is dx, what is dy, and length of the member can be calculated in a manner similar to we have seen for element 1 and element 2, and cos alpha, sin alpha, and EA over L value, and we can calculate what is transformation matrix and local stiffness matrix and the element stiffness matrix in the global coordinate system is given by this one. And please note that the displacements at all nodes except node 4 are 0, and this is what required for assembly of instead of assembling the entire global stiffness matrix, we can assemble directly the reduced stiffness matrix or reduced equation system. So, the global equations will be 2 by 2 after imposing the boundary condition, and this is a 2 dimensional or 2D plane truss problem, and there are 4 nodes. So, at each node you have 2 degrees of freedom. So, final global equation system or global stiffness matrix will be of dimension 8 by 8, but instead of assembling entire global stiffness matrix of 8 by 8, we can actually directly assemble the reduced global stiffness matrix by deleting rows and columns corresponding to the nodes at which displacements are 0. Here 1, node 1, node 2, node 3, all degrees of freedom are fixed. So, the corresponding rows and columns can be avoided. So, actually the contribution to the reduced stiffness matrix will come from the fourth quadrant. If you divide the stiffness matrix of element 1 into 4 quadrants, similarly stiffness matrix of element 2 into 4 quadrants and stiffness matrix of element 3 into 4 quadrants, and if you take the fourth the quadrant and add the components, the corresponding values at the corresponding locations in the fourth quadrant of each of the element stiffness matrices, we will get the global reduced global stiffness matrix. These equations, that is the global equations, global system equations, we can get, can be assembled by simply adding the lower 2 by 2 submatrices for all the 3 elements. Please note that this is true only for this case, because for if you take element 1, it is going from node 1 to node 4, element 2 is going from node 2 to node 4, element 3 is going from node 3 to node 4. So, for all elements 1, 2, 3, fourth node is local node 2. So, that is why this is applicable only for this particular case, or if you carefully number the node numbers, similar kind of thing can be done for other problems also. So, the reduced global stiffness matrix is given by this one, adding up the last fourth quadrant of all the element 1, element 2, element 3 equation stiffness matrices, we get the reduced global stiffness matrix. And the global load vector is nothing but the load vector, the components of the load vector at location 7 and 8. That means, we are removing all the components in the global load vector, which are corresponding to node 1, node 2, node 3, and which corresponds to the locations 1 to 6. So, in removing those, we get the reduced global load vector, which is shown there. So, we have reduced stiffness matrix and reduced load vector. So, we can write final equations, final reduced equation system is given by this, which is a 2 by 2 system. We can solve for u4 v4 and we get the values like this, all are in inches. So, now we got the nodal values, and u1 v1, u2 v2, u3 v3, all these are 0, and whatever is non-zero, that is u4 v4, we just obtained. And now we are ready to calculate or compute element forces. For each element axial force can be computed as before using this one. So, only the first term is additional one, which is contribution from lack of fit. For element 1 we have this term, for element 2, element 3 we do not have this term. So, for first element we must add initial tension to get the final axial force in it. So, for element 1 the axial force is given by the value here, and as expected this value turns out to be positive, which means the member is in tension. That is what is expected, because element 1 is short by certain amount and it is force is stretched and force fitted into structure. So, that particular member will be in tension, and element 2, as I mentioned, element 2 is not going to have P of t contribution, because there is no force fit for element 2. So, P of t is 0. So, the calculations were similar to what we have seen in the earlier class, where there is no force fit, such kind of things, and it turns out that the value of force in element 2 is negative, which means it is compressive. It is expected, because element 1 when it is force fitted, it is exerting compressive force over the rest of the structure, and element 3 calculations are given here, which is also in tension. So, this example demonstrates how to calculate stresses and displacements because of lack of fit, and similar kind of or the procedure will be similar even if the problem is instead of lack of fit, it is due to change in the temperature. So, the procedure is similar. So, now we will go to the next concept, which is the beam bending. So far we have looked at trusses, and next one is beam bending. So, beam bending problem is governed by a fourth order differential equation, and what we will do is we will first derive the governing equation for beam bending problem, and then we need to again the 2 node element for bar element, which so far we are using the same element we are adopted even for truss problems. That element at each node you have only 1 degree of freedom. So, that element is not applicable for beam bending, solving beam bending problems. So, what we will do is we present or we derive finite element formulation for a 2 node beam element, as we did for 2 node bar element. We will be doing for 2 node beam element, but if somebody is interested to derive the finite element formulation for 3 node beam element, the procedure is similar, or similar procedure can be adopted to get the higher order beam elements. So, a beam is a structural member that carries transverse load along its axis, and here a typical beam is shown, and length of beam is large compared to its cross section dimensions. In general, cross section can be of any arbitrary shape, and also it can vary along its length, along the length of the beam. However, what we will do is whatever equations we are deriving, or will in this course we will limit ourselves to cross sections which are symmetric with respect to the plane of loading, and x axis passes through the centroid of the section, and here as shown there, a typical beam lying along x axis and loaded in xy plane is shown there. And one important thing is sign conventions, and conventions adopted for positive directions for transverse displacements, rotations, applied forces, applied moments are shown there in the slide, nodal degrees of freedom and applied forces and moments, and also sign convention for internal moments and internal shears are also shown there. And now as we did for a bar under axial deformation, when we are deriving the Gowning differential equation, what we have done is we have taken a differential element and indicated all the forces acting on free, or we have actually based on the free body diagram of that differential element we derived the governing differential equation. So, similar manner a differential element is shown on which all the forces are indicated, shear forces, shear force, moment and the load on both the shear force, moment on both the sides of the element, and element is of length dx. So, now as we did for bar under axial deformation, we need to apply the equations of statics, that is sum of all forces in the, here forces are acting in the y direction. So, sum of all forces in the y direction should be equal to 0, sum of all moments taken about a point should be equal to 0. So, let us apply the first condition. Sum of all forces in the y direction is equal to 0, that gives us derivative of shear force, spatial derivative of shear force is equal to the distributed load applied, and moment, sum of moments is equal to 0, that gives us that equation, and neglecting dx is small. So, dx square is going to be very small. So, neglecting dx square, we get derivative of moment, spatial derivative of moment is equal to shear force, and the first equation gives spatial derivative of shear force is equal to the applied distributed load, and second equation gives spatial derivative of moment is equal to shear force. So, what we can do is we can differentiate second equation one more time, differentiating second equation with respect to x one more time, we get this equation, and here this equation gives us relation between moment and shear force and distributed load applied or load applied, but we want to solve for displacements because of the transverse load. So, we need a relation between moments and transverse displacements, and moments can be related to transverse displacements by considering beam deformation shown here. Deformation of beam is shown here, and here it is assumed that the displacement V is small, transverse displacement V is small, and plane sections remain plane after bending. And if you look at the figure, a point A located at a distance y from the neutral axis is displaced or shifted to point B. Initially the vertical plane section has rotated through an angle derivative of V with respect to by an amount equal to derivative of V with respect to, or first derivative of transverse displacement with respect to the x. So, that is equal to theta, that is it is rotated by an angle is equal to dV over dx, and assuming u, here two displacement components are shown, u and v. U is in the x direction, v is in the y direction. Assuming u to be positive in the positive x direction, the point A, because of application of load and because of this bending beam deformation, it has moved in the negative x direction. So, u component of displacement of point A is given by u is equal to minus y dv dx. Minus is because it is moved in the opposite direction to the positive x direction, and this gives us relation between what is the relation between displacement in the x direction and displacement in the y direction or rotation. And using strain displacement equation, axial strain is given by epsilon is equal to derivative of u with respect to x. Just now we derived what is u, u is minus y dv dx. So, taking derivative of that we get this, and using Hooke's law, axial stress is given by Young's modulus times epsilon. Young's E is Young's modulus there. So, axial stress is given by this, and if you plot this variation of stress over a cross section, it looks like this. So, this equation shows a linear variation of stress over beam section. The equilibrium at a section requires stress resultant over the cross section must be 0, because there is no applied forces in the x direction. Since x axis is assumed to pass through the centroid of section, it is clear that this requirement implies that neutral axis pass through centroid of section. And also moment equilibrium condition requires that moment of forces acting on cross section must be equal to the applied moment at the section. So, the resulting moment from the stress distribution shown in figure given here results in the following moment curvature relationship. So, taking moment of stress over area dA gives you force over that differential element. So, sigma times dA, and if the force is in the positive x direction, it is tension. If it is in the negative x direction, it is assumed to be compression. So, here the sigma times dA is acting in the negative x direction, and because of that it gives a moment which is opposite to the sign convention. That is why the relation here is m is equal to minus sigma y. Y is the distance of the differential element from the centroid or the neutral axis, and this is for a differential element dA. So, we need to sum up over the entire cross sectional area. So, it is minus integral sigma x y dA, and sigma value is substituted there, and finally it is equal to EI second derivative of transverse displacement. Moment is equal to EI second derivative of transverse displacement. So, this is the relation between moment and transverse displacement, and I here is defined as integral y square dA over the cross section. It is called moment of inertia of cross section. So, now we got a relation between moment and please note that this is internal moment and transverse displacement, and earlier we have seen what is the relation between moment and load applied. So, we can write the rewrite the previous equation and obtain the governing differential equation in terms of transverse displacement by this here basically m is equal to ei second derivative of transverse displacement with respect to the spatial coordinate is substituted, and we obtain this equation, and the governing differential equation is this, and it can be observed that this is a fourth order differential equation in transverse displacement V. So, we require 4 boundary conditions to solve this equation, and the boundary conditions may involve derivatives of transverse displacement up to the order 3 up to third order, and physically boundary conditions have the following meaning. V is transverse displacement and derivative of V is nothing but rotation, and second derivative of V times modulus of rigidity, that is EI, gives you moment, and EI times third derivative of transverse displacement gives shear. So, any of the boundary condition, any combination of these boundary conditions can be given, and 4 boundary conditions are required to solve this problem. And looking at this physical meaning of the terms, and the boundary conditions involving V and derivative of V are essential, and the boundary conditions involving second derivative of V and third derivative of V are natural boundary condition, and this can be verified using the thumb rule that I gave in the earlier classes. So, if a differential equation is of order 2p, those boundary conditions of order 0 to p minus 1 are essential boundary condition, and those boundary conditions of order p to 2p minus 1 are natural boundary conditions. Based on the thumb rule, we can classify the boundary conditions involving V and first derivative of V are essential, and second and third derivative boundary conditions involving second and third derivatives of transverse displacement are natural boundary condition. So, now we got the differential equation, we got the boundary conditions. So, now we are ready to apply variational approach to get the equivalent functional. So, now to find that, the procedure is as follows: multiply the given differential equation with variation of transverse displacement, integrate over the problem domain. Here the problem domain is taken as x1 to x2, and next step is any of the higher terms having higher order derivatives, we can reduce the order of derivative by using integration by parts. And also please note that integration by parts can be applied as many number of times as one wishes to reduce the order of differentiation. So, integrate first term by parts, that gives us this equation, and if you see the second term, which is integral, in the integral, or the first term in the integral is actually having derivative of second derivative of transverse displacement, which turns out to be the third derivative of transverse displacement. So, we can still use one more time this integration by parts and reduce the order of differentiation of that term. And also note that derivative of variation of v with respect to x is same as variation of derivative of v with respect to x. So, since derivative and differentiation and variational operators are interchangeable, so we can write that in that manner. So, noting these points, this equation can be written in this manner. And now wherever e times second derivative of v appears, we can replace it with m internal moment, and wherever e times third derivative of v appears, we can replace that with internal shear, and also we can apply variational identity. We can apply variational identity to reduce or to rewrite this equation. So, this is the relation between internal moment and transverse displacement, internal shear and transverse displacement. In addition to this, we will be using this variational identity, which one can easily verify. So, wherever the right hand term appears, we can replace it with the left hand side term. So, using these definitions of internal moment, internal shear and variational identity, the previous equation can be rewritten in this manner. And here the integral, inside the integral you have variation of inside integral, integrand is in the form variation of u plus variation of v. So, we can try, you can take bring that variational operator out outside the integral, since variational operator and integral operator are interchangeable. So, we get this one. So, now to simplify this equation further, two condition arises if essential boundary conditions are specified and if natural boundary conditions are specified. If essential boundary conditions are specified, please note that for a beam problem, displacement and rotations both are essential boundary conditions. So, wherever displacement and rotations are specified, at those locations variation of those particular quantity, that is variation of this transverse displacement, variation of rotation should be equal to 0. That is what we learnt earlier. So, with that reasoning, the first two term gets cancelled if essential boundary conditions are specified and the equivalent functional So, this is the reason the admissible trial solution must be such that their variation at the corresponding end should be 0. Therefore, use of admissible functions for boundary terms, therefore, with the use of admissible functions the boundary terms vanishes and the equivalent functional becomes this one. And whatever is there inside variation, that is nothing but potential energy, or the potential energy functional is given by when this is only applicable when essential boundary conditions are specified at both ends. Suppose if natural boundary conditions are specified, that is moments and shear forces are specified, we need to substitute those values and we need to simplify the functional that we have seen earlier. natural boundary conditions V and M are specified at either end. In practice, please remember or please note that the equation so far we have derived, V is internal shear and M is internal moment, but in practice nodal forces and moments are prescribed at beam ends rather than internal shears and internal moments. So, we should note down the relation between the nodal forces and moments and internal shears and internal moments. And if you go back and see the sign convention, that we started out with, this is what we started out with. The first figure shows the sign convention for nodal degrees of freedom, that is displacements, transverse displacements and rotations, and also that is the sign convention for applied forces and moments, whereas internal moments and internal shear figures are given as the second figure shows for internal moments, third figure is internal shear. If you compare the sign conventions there, nodal degree of freedom and applied moments or the applied moments at the left hand end is in opposite direction to the internal moment at the left hand end, whereas at right hand end the applied moment is in the same direction as internal moment. Similarly, at the right hand end the applied force is in opposite direction to internal shear at right hand end, whereas at the left hand end internal shear is in the same direction as applied force. So, noting these relations between internal moments, internal shears and applied forces and moments, because of different sign convention for applied forces and internal moments, as illustrated in the figure below, the applied and moments and forces are related to internal moments and shears as follows. So, these are the values or these are the quantities that we need to substitute into the equivalent functional that we have earlier and simplify it further to get the corresponding potential energy functional when natural boundary conditions are specified. Substituting what are the values of V at x1 x2, what are the values of M at x1 x2, we get this relation. And here please note that F1 F2 M1 M2 acts like a constant as far as variational operator is concerned. So, the terms variation of V times F and variation of derivative of V with respect to x times M, those terms can be grouped together, and the functional total functional can be written in this manner. So, the potential energy functional for beam bending problem looks like this. And the functional is known as potential energy for beam bending, and the first term in the functional is nothing but strain energy, bending strain energy. The terms in the functional are usually given by the following physical interpretation. The first term is beam bending energy, second term is work done by the distributed load Q, and the third term is work done by the applied point loads or end loads, which is given by rotation times moment at both ends plus transverse displacement times force at both ends. So, the potential energy functional or potential energy can be written as strain energy minus work done by the applied forces. So, what we have done is we have looked at a governing differential equation for a beam bending problem, and starting with governing differential equation we have derived equivalent variational functional or equivalent functional or equivalent or potential energy functional for beam bending problem. So, to proceed further what we need to do is we need to develop a finite element for beam formulation, which we will continue in the next class.